Okay. Okay. So I'm here. I'm very happy to share some of my recent work. And this one is partly actually a undergraduate research project, and it's about some topics in so-called the extension operator, but not the full extension. So this is his joint work with a Haowen Lu. He's now a graduate student in CUHK. Okay, so let me start. Um, so the extension operators, or the extension problem, it's be described in this way. So let's say if we have a function that it's defined on a domain, and let's say a omega, it's a subset of Rn. The extensions of f is going to be some function which we denoted by f tilde. So a f tilde is a functions that define on the total space Rn, such that if you are looking at back to the omega itself, so if you look at the point x in omega, then f tilde x is actually just fx itself. Okay, so the extension problems, it's finding a way to maps the f to f tilde, and most likely this map is linear, at least for the things that we are talking about today, everything is going to be a linear map. So that's the how we brought up with the extension problem. But we will not need to limit ourselves into discussing just functions. These things make sense as distributions as well. So when we talk about distributions or generalized functions, we can talk about a natural restriction map that map basically we can restrict the distribution to Rn to a distribution omega, because a linear functional on CC infinity Rn is naturally a linear functional in CC infinity omega. So we will have this kind of a restriction map, and then the extension operator can be defined as a so-called right inverse to the restriction map. So if you have a distributions in omega, you extend them and then you restrict them back to the domain omega, it would just be your original distribution itself. So that's how we have the extension problem. Okay. Basically, if you have a domain omega and you have some function space, x can be anything, which we will talk about more later. Could we find a extension operator E such that E maps the x omega to xRn? And more generally, if we have a bunch of classes of function space X, could we find one extension operator that is bounded in all these kind of X simultaneously? And I try to draw a pictures below where you can think about a function's f is defined on the right-hand side, which we let's denote this by omega. So we want to find out an extension operator such that the extensions of f is not a bad function. So think about a purple line here. It's a function that has some kind of singularity. So that is the bad extensions. And we want to restrict ourselves into like the smooth line, the origin line. So this is the good functions. Okay. So that's what the extension operator that we want to consider. So when we talk about the extensions in history, so to begin with, people will actually think about this kind of easiest example, which is called the half-space model. The half-space models is a space where the last coordinate is positive. So it's just like the up half space. And you have a function on the upper half space, and you want to extend it to the lower half space. Okay. The extensions that people start with, it's so-called the Seeley extensions, which takes of this form, where when x is less than 0, so we have a constant aj times your functions f, where at the first n-1 coordinate is the same, but for the xn coordinates, it's going to be, we take the reflection by bj. Okay. So this kind of sum would be finite or infinite, depends on what things we want to look for. Okay. So let me give you a few examples. So let's think about a function, maybe fx is sine plus cosine. So the trivial extensions that we can consider is just the zero extensions. So we have the zero line here, the blue line here, and you can quickly see that this is not a good extension because it's discontinuous. Okay, so it's actually discontinuous at the 0 point. And most of the extension we want to have, at least we want to preserve the continuity. So that's actually not something to begin with. Well, if we think about, okay, so we want to preserve a continuity, what would be the first things that we want to do? We would like to have reflections. Okay. So we'll just take the reflection by defining the EX to be F negative X itself. Okay. So now you actually have the reflections and preserve continuity. But if you look closer, so you can see that at the point 0, x equals 0, the function is continuous but not differentiable. So that tells you that if you want to preserve a differentiability, you probably need to do more modifications. Okay. So the next step we can consider is maybe we want to take some linear combinations. Okay. So maybe let me go back to here. The coefficients or the things we construct, one way to do that is the following. So we can consider the EF to be 3f minus x, 3f negative x minus 2f negative 2x. Okay. So we chose the coefficients 3 and negative 2 so that if you look at its value at zeros, it's the left-hand side, right-hand side coincide. And if you take the derivatives, then by chain roots, you will see that the left-hand side, the left-hand derivative and the right-hand derivative, they will be the same. So that's how we preserve the differentiability. But if you want to do something more, if you want to preserve a higher order differentiability, this is actually not good. So we can actually imitate this process. We think about another extensions. So if you check this extension yourself, you can quickly see that these extensions preserve the continuity differentiability and also second order differentiability. Okay. So that's the basic ideas of using of constructing this kind of extension. And okay, so basically by chain roots, we can see that every time when you take a differentiability on xn, you will actually pull out a negative bj. So you can check that if E maps Cm function to Cm functions, so if we preserve order m differentiability, that's actually equivalent to say that aj times negative bj and raised to the power of k. This thing, when you sum them up, it would always equals to 1. Okay, so for all k, that it's integer between 0 and m. Okay. So that's because basically you pull out the partial derivatives, and then you got aj times negative bj to some power. Okay, and to make sure the left-hand derivative and the right-hand derivative are same, basically saying that after the sum, this should be equals to 1. Okay, so that's how it works for functions. But we don't have to limit ourselves on functions. We can talk about distributions. And let me denote this weird space, C negative M, U. So C negative M, you can think about this just by taking the formal sums of some partial derivatives of C0 functions. Okay, so we take some partial derivative up to the order M, and we just take the sum, we just sum it up. And the norm is actually just given by taking the infimum of all possible decompositions, which is just like really arbitrary and not very natural definitions. And then we say we can check that E would map C negative M to C negative M if and only if the same equation is true for all k, now for all k's between 0 and negative m. So now it's for all the negative integer k that stands between negative m and 0. The reasons why this is actually the case is because, well, previously we pull out the we have a derivative on the outside and we remove the derivative inside. That's how we got. And when we talk about the extensions of distributions, we are sort of talking about the extensions of derivatives of continuous functions. And then we pull out the derivative on the outside. So now we have aj times b negative bj to some negative power. And then multiply with some derivatives, the derivatives of the continuous function. So yeah, now this is one, in order to make it continuous, we are talking about the sum to be 1 for all alpha in between 0 and m. Okay. So that's basically the setup. In order to make the extensions bounded in as much space as possible, we would like to want the algebraic conditions to be true for more integer k as much as possible. And so here is a short history. Previously, for a work that's mostly done by triples, but then if you want to talk about the Sobolev space, this is actually a very easy exercise. And by some simple linear algebra arguments, you can show that if you want to, for every n, you can always find out finitely many this kind of a real number aj and some positive real number bj, such that this equation is true for all k that's between negative m and positive m. Okay. And once we have this kind of conditions, we can see that E is bounded in WKP for k is between negative m to positive m. So basically just says that if you have a bounded range of function space, then you can always achieve this by picking a finite set of elements, aj and bj. So triples work is mostly like generalize this result to all the Besov space and Triebel-Lizorkin space, which we will not cover this in detail here. Okay, but so previously all the discussions only works for finite choice, finite sets of numbers. Also, in 1964, Robert Seeley generalized it to the infinite sequence. So his motivations originally is to extend the smooth functions. So if you have a C infinity functions, you want to use this procedure and to extend C infinity function as well. And here is the one that shows that, okay, so you can choose the infinite sequence aj, bj, such that this sum equals to 1 for all non-negative k. And based on that, you can check that the E would bound it, would map all the classical Sobolev functions to Sobolev functions. And if you let k goes to infinity, you will see that the extension would preserve smooth functions. And then when I look at these problems, it would be actually natural to ask, okay, so the classical results show that we can do things a bounded range for positive and negative k. Seeley's result shows that we can extend all positive k. So could we actually combine them together? Okay, so like, could we find the sequence of aj and bj such that this summations is true for all integer k? Because once we do that, then by some arguments, we can show that the E would extend all the function space or most useful function space. And it turns out that the answer is yes, not just yes, but the proof is actually a undergraduate research project. Okay, so that's how the story begins. Okay, so here is our work. So we show that this is actually the case. We can find out a sequence of real number aj and a sequence of positive real numbers bj such that this kind of sum is equals to 1 for all integer k. And also the sum actually absolutely converge. And then as a result, when we construct the extension operator in this form, this is actually an extension operator that it's bounded in all the ck space and all the wkp spaces for all integer k and for all p in between 0 and infinity. So here the ck spaces is a classical like k order differentiable space when k is bigger equal to 0. For negative integer k, you can think about the space that I just defined earlier, or you can just take other definitions, whatever, which one that you like. And similarly, for p that is less than 1, the space actually also makes sense, even though it's actually not the space of distributions. So whenever you actually chose a suitable definition for those space, this E is actually bounded in those function space as well. So this is actually an extension operator that extended all the CK space and all the WKP spaces, and we will call it universal extension operator, which I will talk about it probably at the end of my talk. Okay, so I want to briefly talk about the strategy of the proof. But before that, maybe let me talk about how the classical cases are proved. So if we want to construct the only finite sets of AJ and BJ, so say we want to find out, so the idea is that actually no matter what BJ that you chose, you can always find out the AJ such that this AJ times b negative bj to the power of k equals 1 for all k between negative m to positive m. The reasons of that is that you can write down all this AJ into a column vectors, and then this is actually to solve the AJ, assuming we have a BJ. Okay, so we actually solving this matrix equations, and then we can by linear algebra, the square matrix on the left hand side is actually invertible. And not just that, we will actually have a really beautiful product formula that can express them. So this is called the von Neumann matrix, and we can use the primary roots to actually write down a very concrete expressions. So this is actually how I'm able to write down the formula here. So basically, I imitate the constructions, and I make this GeoGebra picture files. This is actually how. If we chose a different m, then we can construct it in this way. Okay. Okay. So let's move on to the infinity cases. So when we talk about infinite cases, we cannot just solve an infinite dimensional matrix. So Seeley's idea is that, okay, since we are doing things on infinity, we actually have more wiggle room and chose a j. So to start with, we can choose a good enough BJ, where Seeley just chose it to the exponential series. So we just fix a beta bigger than 1, and we take BJ to be beta to the power of j. Now, to find AJ, it's actually to solve the equations where sum of AJ times beta to the power of jk equals to -1 to the power of k. Okay. So we just pull out the -1 to the right side. So if we look at the sum on the left-hand side, we can actually think about this as a holomorphic functions, which takes the value beta to the power of k. Okay. So this is a holomorphic functions that define in the whole space. Okay, so it's actually an entire functions. And we are looking for entire functions f such that on beta to the power of k, this is -1 to the power of k. So finding AJ is actually to find these entire functions. So this is actual classical complex analysis interpolation problems, and this one can be resolved by Weierstrass factorizations. Okay. And then when I gave out these questions to Haowen, and he realized that okay, so first, what we want is to generalize Seeley's results from non-negative integers to all integers. Okay, so that's the goal. And immediately we can notice that you cannot just casually generalize it to the sum for j from negative infinity to positive infinity, because this is actually not the entire functions. It will actually have essential singularity at 0. So this is actually not something that we want for some natural reasons. Okay. And then Haowen quickly realized that we actually don't need a j from negative infinity to positive infinity. We can still reduce the problem to finding a holomorphic functions. So since we are choosing bj, we're still choosing bj to beta to the power of j, where j is all the integer, but we can also force aj to be an even series, meaning that aj and negative aj are the same. So in that case, we only need to think about a sum from 0 to infinity. So the problem we try to solve is actually this one. Now it's a0 plus aj times beta to the power jk plus beta to the negative power jk for j from 1 to infinity. Okay. And so basically we are now looking for this holomorphic functions f such that on beta to the power of k, it's -1 to the power of k minus f at the point beta to the negative power of k. So now this questions become, if you actually look at the right-hand side term, f negative, f beta to the negative k, this is actually a remainder term. So it's actually like a small term, and we can think about this like a contraction mapping sequence. So what we are doing is that, okay, so we can think about f to be, this is maybe at the end step, and this is actually something we want, and the right-hand side is like the n-1 step. So we will construct this by looking at a contraction mapping sequence in L infinity, little L infinity. And each step we look for a GU, that's a corresponding entire function, such that at the point beta to the power of k equals to UK. And yeah, so we actually have a linear way to map sequence U to the entire function GU. Okay, so we start with U0 equals 1/2 and UK equals -1 to the power of k, and then we fit in as the iterations. So for the union plus one, the new plus one sequence, at the k terms, it equals to -1 to the power of k minus like the new g functions at the point beta to the negative k. And so we are constructing a sequence of entire function in this way. So at the new plus one, we take the solve the interpolation problems at the beta to the power of k, and this is equals to -1 to the power of k minus the previous remainder term. And by choosing the beta to be suitably large, actually when it's larger or equal to 4, this is actually able to solve the problems. So we actually get a construction map, and we know that it always converges into some little L infinity sequence, and that limits it's actually something that we want. Okay. So this is the undergraduate research project parts. Well, for the rest, this is actually something that kind of hard, and since the proof is actually not very elegant, so we're going to skip here. So basically, the slightly harder part is to show that once we have the extension, once we have this sequence, the extension operator, it's actually bounded in all the so-called Besov space and the Triebel-Lizorkin spaces. Such extension operators, which bound in all the Besov and Triebel-Lizorkin space, is so-called the universal extension operator. And our construction is actually the second ones that prove that construct the universal extension operator. And previously, the only known examples is the one that's done by Richkov in 1991, where he's actually something that uses little Paley decompositions, and it works for Lipschitz domain. But the construction itself would be much more complicated than the half space extension or the Seeley extension that we're using here. Okay. So yeah, that's all the things we'd like to talk about. And yeah, I would like to end here by bringing up some open problems. So the Seeley extension, it's this extension that bounded in most of the function space, or the function space that we would like to work with. But it's actually not true that it's bounded in all the function space. For example, it does not extend the real analytic functions. Well, just take the functions e to the negative x. So this is a real analytic functions on the whole real line. But then, since we know that the extension operator preserves boundedness, the extended functions, it's actually a bounded functions. But e to the negative x, if you extend it to x goes to negative infinity, this is actually goes to positive infinity. So this is actually not a bounded functions. So the extension operator that we are talking about here never extended the real analytic functions. So this is actually still a gap between smooth functions and real analytic functions. And also for polynomials, you can check that it actually extends polynomials. Okay. So there's something in between where it fails to be bounded, and we want to ask, okay, so whether or not we can find a critical space for which the extension operator is bounded. We can think about so-called the Jerry class, which is a class of functions that it's between real analytic functions and smooth functions. So once we can prove that maybe if the extension is bounded in this space, then we will be bounded in its dual space as well. So we will actually prove its boundedness on a larger classes of distributions, so-called maybe the ultra distributions. So that's the open problem that I'm kind of interested into that, and I'm very happy to discuss it in detail if you are interested. Okay, and thank you for your attention.